speaker is supposed to be me, but Vishnu has very kindly agreed to swap with me. So next speaker is Vishnu, who will tell us about the colored Jones polynomial and the volume conjecture.
All right, thank you. Let me start by thanking my co-organizers for this meeting. I'll tell you about some work I've been doing on colored Jones polynomials. So this is work in collaboration with Mark Hughes, who's a dimensional topologist at BYU, and then Ramadevi Bombay, and Pratik Roy, who is stuck in India at the moment, is not here, and Vivek Singh at Abu Dhabi. So this is a string meeting, but there's essentially no string theory in this talk. This is about mathematics and about shared assignments theory for the most part. So we're thinking about knots as an S1, which is embedded into three manifold. For my purposes, I'll take it to S3. And these knots have been classified in various tables by mathematicians up to about 19 crossings comprehensively. So these are the first few knots at 0, 3, 4, and 5 crossings. And these tables have a long history, and the crossing number is a proxy for the complexity of the knot. And the number of knots at a given crossing number grows extremely fast, exponentially in fact. So at 9 crossings, you see a lot more knots, and this of course keeps going. So by crossing number, we mean minimal crossing number. We always include twists that artificially inflate the crossing number. In fact, you do a bunch of Mandelstam moves that makes a knot look more complicated than it initially is. This means that even the unknot, if you look at various complications by applying Mandelstam moves, it's very hard to identify just by inspection that you have no knot at all just by looking at the projection or this knot diagram that we have here.
Sorry, why are there names for these unknots? I mean, this is an unknot, right? I mean,
It's an unknot. These particular twists have names for whatever reason. There's also a Gordian unknot that's of interest to mathematicians, I suppose. Yeah, they've got names sometimes. In fact, the complications associated to these Radameister moves are such that the original little knot table from the late 1890s had an error in it that was not realized until 1973. So these two knots which appear in the table at 10 crossings, 10-161, 10-162, are in fact the same knot. People tried to distinguish these knots using various methods. They found that they were always giving the same quantities. So eventually, Perko found the right Radameister moves to move this knot into this knot. So these, by inspection, it's extremely difficult to even make sure that your list is A, complete, and B, unique. So this has always been a problem in generating these lists statements.
So in the beginning, why were they classified differently?
I don't know. They look different. So I imagine that they tried to do these moves. They didn't find the right set of moves in order to convert.
Because I would imagine that the other event was more likely that you see that two knots that are classified the same because various things evaluated the same, but they happen to be different. And
that can also happen. I'll get to that briefly later on. It's one of the open conjectures that I'll address. So eventually, it was determined the way to identify knots with the signature was to compute topological invariants for these. So these topological invariants are, of course, independent of how the knot is drawn, and one such invariant is a Jones polynomial. So there was a combinatorial way of constructing the Jones polynomial that Jones developed in 1985, and the Jones polynomial is normalized so that the Jones polynomial associated with the unknot is 1. Witten realized that you can calculate. So this W is a Y. It's the number of overheads minus underheads, and then there are these so-called. If you just look at the knot diagram, how many times is there a crossing above? How many times is there a crossing below? So that's where this exponent comes from. And then the so-called scheme relations, which let you simplify this move into these two things. You can apply these scheme relations in order to construct this this invariant, and then you take the ratio of the unknot to get the actual polynomial with this weighting factor in front. There's also some issue of framing that I won't get into, but there's some prescriptions for running these Jones polynomials in this way.
Can all the knot invariants be defined through some scheme relation?
No.
Was Jones polynomial the first knot invariant?
No, there were not invariants before this.
I see.
This is the first useful polynomial, well, the Alexander polynomial came first actually. So there are other polynomial invariants that people look at. This one's particularly useful.
And does this one have the property that any two different knots have different polynomials?
No. That will also come up later on. So we don't have a simple set of invariants in general that distinguish two knots from each other.
I see.
So you need either a list of invariants to do this, or very complicated invariants that are not very tractable to play with.
So Vishnu, if I want to write down scale relations using which I want to construct invariants,
Yes.
then they presumably satisfy some sort of consistency condition.
Yes.
It's some invariants and
Yeah.
So have people try to solve that system and try to construct general scheme relations?
Yes, they have.
No.
So a lot of the stuff has been very well explored here. It's just one of the new things we're able to do is associate different invariants to each other and see what these connections are. And this is one thing that machine learning is particularly good at. Okay, so the topological invariants, the Jones polynomial in particular, we calculate from Chern-Simons theory. So in Chern-Simons theory, natural operators look at Wilson loops. We have a capital-ordered exponential of the holonomy over some closed loop. And if we take this closed loop to be the knot, you can construct the so-called color Jones polynomials. Color refers to the representation of SU2. So these ends index the number of boxes basically in the Young diagram. So in my notation, J2 refers to the fundamental representation, the ordinary Jones polynomial. J3 is the adjunct representation, the first colored polynomial. But there's an infinite list of these for SU2. We just compute these as correlators in the usual way. And we have this Chern-Simons action, and the level in front is integer quantized so that this action is gated. Okay, so the Jones polynomial, for example, for the figure 8 knot is this expression here. This Q which appears is either 2 pi I over k plus 2. K is that level for the Chern-Simons theory. The plus 2 corresponds to the dual Coxeter number of SU2. So an open question is whether the Jones polynomial is the uniquely identifies the unknot. So the unknot I told you was normalized to the Jones polynomial. The unknot was 1. We don't know whether there's some other knot with Jones polynomial 1 as well. And this is an open question, and the unknot recognition problem is not even known whether it's NP, but this problem has a long history with Dan and Turing and Hawken and Rackenby, most recently studying this. Recently, people have been applying machine learning to this to try to construct a knot with the same Jones polynomial as the unknot, and these attempts so far have not succeeded. So people who've been doing this are Sylvia Ducal and Jim Alberson, and Victor Sylvester. They've been looking at this unknot recognition problem using machine learning methods.
Sorry, about this NP comment.
Yeah.
So NP means you have to check an answer in polynomial. So what is the answer you're checking? A yes/no answer or a sort of algorithm to unknot it?
The algorithm.
Huh?
You're checking the algorithm. Okay, so another knot invariant is the hyperbolic volume. So these knots in boxes are so-called hyperbolic knots. What this means is if you take a tubular neighborhood around the S1 embedded in S3, you subtract out the tubular neighborhood. This is called a knot complement. If that knot complement admits a metric with constant negative curvature, the knot is said to be hyperbolic, and the volume in that metric is a knot invariant. So this was realized by Thurston. This is part of his geometrization program in order to classify all 3 manifolds, and uniqueness is guaranteed by this Mandelstam rigidity. So this combination of results means this is an interesting invariant to look at, and Thurston told us how to compute this in the so-called tetrahedral decomposition of the knot complement ideal tetrahedron.
So it's defined for all knots?
It's defined for all hyperbolic knots, not all knots hyperbolic though. So there are torus knots, satellite knots, hyperbolic knots, and every knot is one of these. This is actually the next slide. If you look at the first 1.7 million knots, all the knots with 16 crossings, all but 32 of these are hyperbolic. So there's a conjecture due to atoms that says the proportion of hyperbolic knots approaches 1 as the crossing number approaches infinity. It turns out this conjecture is false. So this was only realized a few years ago by Mandelstam, that the number of satellite knots over the number of prime knots, that ratio is bigger than 1 to the 2 times 10 to the 17 in the limit that crossing number goes to infinity. So there's a danger here that one should be aware of, in that if you're looking at data sets with small crossing numbers, say, which is what the data sets we have access to are, then the conclusions you draw from these data sets may not be universal data sets, because the behavior of knots themselves changes as a function of crossing number. So you should keep that caveat in mind when we're looking at these data sets.
So, Vishnu,
Yeah.
do people know anything about PM and the element limit?
Like what the statistics are?
Just how it behaves with them?
I think it behaves exponentially, the number of prime knots, right?
Yeah.
There's if you plot the data points for how many knots there are at each crossing number, it fits to an exponential graph.
I see. But there's no analytics results.
I think they're asymptotic results. I don't
Yeah,
know.
so asymptotic,
Yeah.
yeah.
I think there are some. I don't know what they are offhand, but I think there are some.
I'm just wondering how would one even approach such a problem with infinitely many large number? In what sense the problem simplifies?
I don't know the details of it. But I think people have looked at this kind of thing.
So, Vishnu,
Yeah.
what are these satellite knots?
So satellite knots are knots such that the knot complement contains an incompressible boundary torus. So there's some definition like that. Okay, so the current state of the art as far as complete tabulation, I think goes up to 19 crossings. There's some results of 25 crossings, but I don't think tabulation is complete beyond 19. Okay, so given all of these things, there was the volume conjecture, which Kashev, Murakami, and Bukov developed. And the idea is you take the colored Jones polynomial, you evaluate it at a current root of unity, and you take the limit as n goes to infinity. This expression, this valuation, will cover the volume. If you remove the absolute value, you'll also get the so-called Chern-Simons invariant from this generalized volume conjecture. In fact, when you take this n goes to infinity limit, as we'll see later on, you also need to take a k goes to infinity limit in the Chern-Simons theorem. Now, if you look at the behavior of this left-hand side as a function of n, there's some knots which you can calculate colored Jones polynomials analytically. And one of these knots is this 18 crossing knot called k0. It's considered a simple knot. It's simple not in the sense it has a few number of crossings, but it's simple in the sense that you need only 4 ideal tetrahedra to compute the volume of the knot complement. So if you do this calculation, you find that there is a convergence of the value predicted by the volume conjecture. This convergence is not monotonic. It's in fact rather slow. So this non-monotonicity means that if you just think about evaluations of the Jones polynomial of small color, it's not necessarily guaranteed these evaluations give you the volume.
It's pretty monotonic once you cross that.
Once you cross that, yeah. But you get fairly bad before you get that.
So when one says volume in this case, one actually gets the finite volume or one has to renormalize?
So if you get the finite volume, which is
Because it's a cusp, right? There's no, you don't have to renormalize. It's in counter.
I don't think there's no counterfeit. I think it's just a direct calculation that gives you this.
Yeah, what does this actually mean, this volume? Like you take the S3 and you remove some cubular neighborhood. Doesn't it depend on how much cubular neighborhood you remove?
I mean, you take a tubular neighborhood of size epsilon and take epsilon goes to 0, and you get some finite answer to the number.
I see. So why is that fine? Why is that much the volume of S3? Like why epsilon goes to 0 doesn't have volume go to 0?
The complement then has some metric. You just compute the volume in that
The
metric.
volume of the complement.
Oh, I see. So volume of the complement in the hyperbolic.
Yes.
I see. And you compare it to the volume of, I see. And that volume is.
Yeah.
And why do you have to take k to the equal?
I'll get that.
Okay.
Okay, so one of the things which is surprising about the Jones polynomial, if you just think about this from a Chern-Simons perspective, is the coefficients that appear in the expression are always integer. So the explanation for why these coefficients are integer is because they are dimensions of things. So there's Colonel homology theory, such that the graded Euler characteristics of Colonel homology is the Jones polynomial. So because these gradings are based on cohomology groups, the dimension there are these integers that appear in this polynomial. So it was noticed, so this categorification was talked about Kavanagh, but really explain what this paper of Kavanagh taught. It was already noticed, if you look at evaluations of the Jones polynomial at the root of unity predicted by the volume conjecture, you get some roughly linear relationship. And similarly, a quantity in Kavanagh homology also looks roughly linear. So there's some relation between the volume, even at maybe small representation that was noticed by Dunfield and then this work was by Kavanagh. These are numerical investigations with a small number of nodes. And we'll try to apply these things with the neural network. So I presented to you a bunch of characters in knot theory and Chern-Simons theory, and the 6 characters in search of an author is a famous absurdist play by Vishnu Jejjala, and here the author is the neural network. So we remind you that neural network tools date way back, 1957. Rosenblatt in the Cornell Aeronautics Laboratory and the Naval Research Lab was looking at so-called perceptron models. The idea is you have some input, you weight the features of these input by different amounts, and you have this neuron, perceptron, and then you act with nonlinearity at this perceptron, and this models the answer. So the nonlinearity you typically use are the heuristic sigmoid. These days, this is the most popular one, the rectified linear unit, which you know uses cache. All of these things work similarly in practice. So if you add a bunch of perceptrons together and connect everything, you get this fully connected neural network. And the idea is you have some vector in some vector space going to some other vector space, and you, in order to go from here to here, you act with weights, some matrix acting on the previous vector, plus some bias, and then you evaluate element-wise this nonlinearity in order to construct this new vector. Then you do this iteratively over several layers, and then you can then construct some function by composing these maps from one layer to the next layer. So these things, okay, so you said this. The weight matrix is a bias vector. The dimension of the vector space tells how many neurons there are in a particular layer, and then there are a bunch of layers. And you compare the prediction at the end of this this neural network to what's called the ground truth, the answer that you have. And then you tune these weights and biases in order to minimize some loss functions during training. The loss would be, for example, the predicted value minus the actual value modulo squared. And when this is 0, the neural network is making predictions with perfect accuracy.
So V L to the power n.
So this is just a sum of the elements of this last vector.
Oh, m is an index, not power.
It's an index, not a value.
Oh, okay, thank you.
Usually you don't want to push it all the way to 0, right? Then you probably move it.
You do overfit it. So you
You want to like see when the training.
Well, the training of the test behavior looks the same. Yeah. Okay, so the neural network models we initially tried, we just took the Jones polynomial and predicted the volume. So the input was just the minimum degree, the maximum degree, and the coefficients. And the data set with 15 crossings, this vector was at most length 18. So these were the inputs, and then we just used a simple 2-layer neural network in Mathematica, the mean squared loss function, which is sigmoids. So this is work with Arjun Kaur and Karparkar. And we found that
What is the, can you say?
the input is just the coefficients in the Jones polynomial, along with the minimum degree and the maximum degree. And if there aren't 18 of these, you just fill it with zeros at the end.
Okay. What are you trying to find it?
It's the volume.
What?
Yeah. So it's actually 2 lines of Mathematica to do this. The rest is just getting the right structures in.
So Mathematica has that built in.
It's built in now, so it's very easy to play with. So this is the actual one. So you see that this is a loss function during training, and it's getting smaller and smaller as the training proceeds. So it's
But your data set is what is your is a table of how many 100,000.
the data set here is 10% of all the Jones polynomials up to 15 crossings or 16 crossings in this experiment.
And what's your test data set?
The test data set is 90%, which I'm not using for training.
For training is 10, the test is 90, but
Yes.
you usually do training 88.
And this works really, really well. So it suggests there's an analytic thing going on in the background.
But if you did it the other way around, you're saying it wouldn't work well? The usual
Typically, you use 80% for training and 20% for testing. But that's because, in this case, even the very, very small training set, you get very good accuracy.
Isn't this better so?
This is even better.
I mean, it's better, but I'm surprised that this, yeah, I mean, this is really
Yeah.
I see.
So, you know,
I get puzzled with the comment. So you said that maybe something analytic going on.
I'll show you.
But no. But what I mean is that the neural networks are not necessarily good at finding analytic functions.
I'll show you how we do this. Okay, so with 10% of knots up to 15 crossings, so 10% of 31,000 knots, 313,000 knots, we get a prediction which is right with 2.4 plus or minus 0.1% error. So
You need 2.45%.
2.45% error plus or minus 0.1% depending upon which data set you provide for training. Okay, so we sort of noticed that if you take the volume, it's a function of the Jones polynomial plus fault corrections. So we observe the Jones polynomial does not uniquely identify a knot. For example, the figure 8 and this knot 11 crossings have the same Jones polynomial with different volumes. In data set with the 313,000 Jones polynomials up to 15 crossings, only this many are unique. When you have this non-uniqueness happening, the average spread in the volume is about 2.83%, which is about as well as the neural network is doing. So it's doing as well as can be expected. The same applies to 16 crossings. We have 1.7 billion knots. There are roughly half of these are unique polynomials.
So when
Yeah.
there are degeneracies, then it picks the volume that it shows is matches with one of them better than others or not necessarily?
Not really, no. It just sort of
Averages, you think? Or?
it's just the average typically. That's what it provides. Okay, so there's a theorem by Sidenko and Hornick called the universal approximation theorem. It says that a feed-forward neural network with a sigmoid activation function in a single layer with a finite number of neurons can approximate any continuous function on a compact subset of Rn. So this theorem says there's a finite number, but it could be a very, very large number. Yes, Bob?
So in your plot, it looks very linear, right?
Yes.
Plot of Jones polynomial versus volume.
Yeah.
Yeah, volume versus prediction or prediction from you. But what is the input you just in the
So this plot's a bit misleading because each point on this plot is a knot. But if you look at a density plot, it's very, very close to this line. I'll show you a density plot in a bit.
So,
Yeah.
why is the slope of the line is not one?
It's one.
It is one. This is predicted versus actual volume. It's just sort of rectangular instead of square. Slope is one.
yeah, so what I mean to ask is that are you feeding the Jones coefficient of Jones polynomial? Is that what are you feeding to the neural network or the whole?
I'm feeding the complete data of the Jones polynomial. So minimum degree, maximum degree, and all the coefficients. So I can recover the Jones polynomial from my input. Okay, so part of the surprise here is simplicity of the architecture that does the job, and the fact that we can learn these things with a very small number of inputs as opposed to the standard 80-20 split. So we want to see whether we can translate this into something which is not machine learning, something which is more analytical.
By the way, if you change the architecture, do you get better accuracy? And you can
It's basically unchanged for this. You add more layers, add more neurons, you don't really get much improvement. It's roughly the same. If you add more for training, then the improvement is there. I'll show you that too in a bit.
So Vishnu, what if you change the machine learning algorithm? rather than doing about some other stuff.
I haven't played that.
Forest or whatever.
I haven't thought that. So we want to reverse engineer your network to obtain something which is more analytic. And we want to interpret this formula, and we can do this with the analytic transcendence theory. Okay, so when we were playing with this, my student noticed that if you just include the coefficients, but not the degrees, results are essentially unchanged. So you're putting in an input from which you can't recover the Jones polynomial, getting the same answers. So because you're just feeding the coefficients
Why
and
can't
not...
we recover the Jones polynomial?
What?
Oh, because the degree, oh, I see, the degrees are fed as special.
Yeah.
I see.
It's part of the input, so I don't include that. I get the same sort of good fit. So this suggests that if you evaluate the Jones polynomial at a phase, then this may be where the degrees don't matter.
Right.
So we then evaluated the Jones polynomial at various phases, and we use a technique called layer-wise relevance propagation. This technique basically assigns a relevance score for each neuron and for each input feature. And we see which relevance scores are the ones that lead to the prediction. So in practice, so this is a different, so each column here is a different knot, and each of these rows correspond to different phase evaluations. Red is more relevant, blue is less relevant. So here, for example, the same phases light up. So we tried various different knots. We found that the same input features light up that correspond to particular phases. So we just used those phases. We found that for the Jones polynomial, a particular phase, either 3 pi or 4, works really, really well. And if you just use this evaluation and fit it to some curve, this also approximates the behavior of the neural network as far as its accuracy goes. So
Now the input is only one number.
it's the evaluation, the magnitude of the evaluation of the Jones polynomial at this phase.
Just that.
Just one number.
I see.
And it does really, really well. And we can use, so we use layer-wise relevance propagation to determine the best phase. If you take this phase and think of this as q equals either 2 pi I over k plus 2, the k this corresponds to is fractional. It's a fractional level if you want to interpret this as the q that you have. Okay, so this is the evaluation at various different phases. We find this phase, either the 3 pi I over 4 works the best, but there is some bad behavior at integer levels and good behavior at phases.
So is it really even 3 pi or 4? Is it something near that?
It's something near that, but I'm just going to take it to be 3 pi over 4. I'll show you why when we compare it to the color Jones polynomial. Okay, so
3 pi over 4 is not less than 1, right?
what?
3 pi over, I don't understand your graph. So
3 pi I over
3 pi over 4 is not less than 1. Where is the right?
less than pi. Last is pi, not
It's
pi.
pi.
Oh, okay, there's 2 different axes. What is the bottom axis?
The bottom axis is the phase.
Oh, I see, okay.
The top axis is the level corresponding to that phase.
Okay, thank you.
Okay, so to interpret this result, we look at the analytic continuation of Chern-Simons theory that Whitten described in 2010. And in part of this analytic continuation, we promote the gauge group from SU2 to SL2C. We also promote the level to be something which is analytically continued. And then we appeal to Moore's theory and work with Lifshitz symbols. We find the path interval evaluated on flat connections depends on a single parameter. The parameter gamma is a ratio of n minus 1 over k. And this answers your question, why do you take k to infinity as well, is because you want to keep this gamma fixed in the semi-classical limit. So as gamma is varied, the analytic continuation picks up contributions from new critical points. There's Stokes phenomena that appear in the complex gamma plane, and Whitten told us how to address these kind of things. And then we can sort of interpret this graph we saw previously. This plateau, this region here, is just corresponding to the latent correlations of the data set. If you compute the volume of any knot as the average volume of the entire data set, that'll give you a 12% error, which is what you're seeing on this plateau. The minimum, these Lefschetz symbols, they contain what's called a geometric conjugate connection, which you expect is in the classical limit, and this is sort of why this particular phase turns out to work so well. And then we have this this dip where the knots retain the geometric conjugate connection even as for many knots, but not all knots. And then we have the spike. And the spike corresponds to this integer level, and the integer level means you do very bad. And effectively what's happening is that in the integer level, the approximations you're doing structurally fail. So what I mean by this is that the approximation formula works with this geometric conjugate connection, and roughly the contribution looks like the evaluation at this geometric conjugate connection times 1 minus e to the 2 pi I k. So for integer k, the evaluation doesn't really help you. So the fractional level is really essential to getting a good approximation.
So just to understand, so from this experiment you found out that level 2 by 3 works best,
Yes.
and now we want to understand
why maybe.
why that
And
is.
witness analytic continuation to provide some
So
explanation.
what is this geometric, this thing? What does that mean, geometric conjugate? How do you
So it's a flat connection that sort of extremizes the action.
and that happens only at that level?
It happens for various knots at different places. So it's not a universal feature, but it seems that the geometric conjugate connection is well approximated for most knots at this particular phase. That's the interpretation we have. Okay, so this is work with Jessica Craven, Archie Corin in 2020 roughly. Now we want to see whether we can do this similar story for colored polynomials. So in order to evaluate the similar thing in colored polynomials, we need the colored polynomials to begin with. So we need to construct these because they haven't been constructed systematically for representations of SC2. So we'll use the braid group in order to do this. So the braid group has generators to satisfy certain algebra, and two closed braid equivalents related by so-called Markov loops. This Markov loop is conjugation. This Markov loop implicates the braid group with one extra strand. And we have taken invariant polynomials by constructing representation of the braid group and defining things which are invariant under these Markov loops. So the Yang-Baxter relation we realize as a braid relation, and we'll use the technology of Yang-Baxter equations in R matrices in order to compute the data set of colored Jones polynomials. So Akutsu and Logati told us how to do this in terms of these exactly solvable models, and we can construct invariant polynomials using the braid group. And these translate to some n-state vertex model, and the invariant polynomials we're after are related to traces of matrices in this thing. So the n equals 2, this, change notation from little n to capital N for color. For 2 color, the 6 vertex model computes Jones polynomials. For 3 colors, you get a 19 vertex model to compute the adjoint Jones polynomials. And if you have a braid with n strands, this corresponds to an end of the n by end of the n R matrix, which satisfies the Yang-Baxter relation. So because of this the scaling, you can only do calculations up to 7 strands. When we've done these calculations, we construct data sets of adjoint polynomials. We get 92% of them at 13 crossings, and then some fraction of them at higher levels.
What's the adjoint Jones polynomial? What's the adjoint Jones polynomial?
I just mean the Jones polynomial in the adjoint representation. So the colored polynomial, I have a trace with respect to some representation of SU2. I take the adjoint representation.
I see. So there's something very basic about that. And you already got a good estimate for the volume using this Jones polynomial.
Yes.
So now, what is the advantage of going to these colored polynomials?
So there was this plot I showed you of K0,
Yes.
which was non-monotonic.
Yes.
I want to see whether, if I use the adjoint polynomial, things improve substantially or things get worse, for example. I don't know the answer a priori. Okay, so given these data sets, we can start playing some games. So here are the zeros of the ordinary Jones polynomial. So it was conjectured by Haust that if you take the Alexander polynomial, the real part of the zero of the Alexander polynomial is always greater than -1. It turns out this conjecture fails, but since then people started exploring the structure of zeros of these polynomial invariants. It turns out the Jones polynomial zeros should be dense in the complex plane. I've only plotted out these zeros up to the knots in my data set, so this is why it's not dense. The colored polynomial, this plot looks rather different. I don't know what to make of this yet, but there are differences in structure zeros for these polynomial variants. And then I can plot the minimum degree of the Jones polynomial as the minimum degree of the colored Jones polynomial, and I get some roughly linear relationship. Similarly with maximum degree. And I can plot the minimum degree and the maximum degree of the Jones polynomials. These are roughly Gaussian shaped. So there's some structure in these polynomials. This is the length of the polynomial, so maximum degree minus minimum degree plus 1. This is the curve for the ordinary Jones polynomial. This is a similar curve for the colored Jones polynomial. The spin's very linear, so we just observed this, and I was talking to Sergey Hukov last week with Spring Data. He thinks he's got an explanation for why these patterns are there in this data. This is related to how these polynomial invariants are computed using these star matrices.
So what is length? What is the y-axis? Polynomial length maybe?
Polynomial length is maximum degree minus minimum degree plus 1. So the dots are the mean, and then the error bars are one standard deviation in this data set. So this is a function of crossing numbers. So I take all the knots with 10 crossings, and I plot the mean and the standard deviation. It's extremely, the data set, well, I mean, it's very linear.
Vishnu, one
Yeah.
question. Is there a way to reduce the size of the error bars, say by increasing the number of samples or something like that?
This is not sampling. I take all the polynomials of 10 crossings. I compute their
So-
the mean length
My
and look at
question is-
standard deviation.
So
There's
these error bars are computed in which way?
I don't know how many, so say I've got 10,000 knots in my, at say 100 crossings. I take the mean length of all those 10,000 Jones polynomials, and I compute the standard deviation. That's what I'm plotting here.
So if you have 20,000 of them, then
There are only a fixed number of them. There's no, if you have 10,000 more, there's a given number of
Oh, I
knots in a
see.
given crossing.
okay. So that means there is no way of controlling the error. I mean, it's given to you.
I mean, it's not an error really, it's a standard deviation that's corresponding to the features of the data set you're studying. This is not, statistical error or anything like that. This is just the spread in the actual data you've got.
So here, the question is not necessarily that it's growing, right? But that it's growing linearly.
Yeah.
That's the.
Yeah.
And at each point, does this have tails that can spread also, this distribution?
I
You
have
have
looked at
the-
that. I don't know.
Not that
I don't know what the tails look like.
tails.
So there's something I just confused right earlier.
Yeah.
It's a thing I would ask something like this. The colored Jones polynomial is when you take this cube itself to mean some representation of
So the colored Jones polynomial is we look in Chern-Simons theory, and you just change representation in which you're taking the trends. So you're looking at SU2 Chern-Simons theory, you're working the phone representation as the ordinary Jones polynomial, to work in the adjoint representation as the Jones polynomial blocking out.
Oh, I see. But if you had a mathematician who didn't know about Chern-Simons theory, how would you have defined this colored Jones polynomial? Because you earlier defined it in terms of
Right. So if you calculate some more complicated scheme relation, maybe you're able to construct the colored Jones polynomial as a mathematician. The translation of Chern-Simons theory enabled all these this infinite number of new polynomial invariants. That was the physics observation that preceded the mathematics observation. It seems to me.
Yeah, well, this came after Newton's theory.
Okay, so another thing you can do is you can plot the evaluation of the Jones polynomial at the phases associated with the volume conjecture. So if you take the third root of unity for the adjoint polynomial minus 1 for the fundamental polynomial, it's a quadratic relation between the evaluations of these different phases. Okay, so
These phases.
what?
How did you pick these phases?
These phases are just the ones
Oh,
that
I
are
see.
put together in volume
I see.
projector. So if you take, so this is 75% of that data used for training, rather than 10%. There the error is 1.65% with the ordinary Jones polynomial. And then if you use the colored Jones polynomial in the ideal representation, this error becomes much smaller, 0.40%. So the improvement with adding these this extra color means the performance, the convergence of the volume conjecture looks very, very much better. You can also look at phase evaluations, and again, at integer values at a level, the prediction does very badly, but there's a best phase here. This best phase turns out to be either 8 pi over 15, the adjoint polynomial. This corresponds to a turn Simon's level of 7/4, where this gamma equals 8/7. And you can then, since you have 2 data points, you can guess the formula for pattern colors. And the guess is that the phase is 2 pi I n plus 1 over n times n plus 2. And you can look at the limits of this, and goes to infinity, and it's the kind of limits you expect for the volume conjecture while all these things happen. So then, you can take different knots and evaluate at the phase I predicted. So the blue is the phase predicted with the volume conjecture. The orange is the phase in the previous slide, and it converges better for figure 8 knot to the actual volume. But you try the K0 knot, the one which suggests that there may be non-monotonicity. The new phase I predict doesn't do any better than the old phase I had from the volume conjecture. So maybe there's a better guess I can make that also improves convergence for this K0 knot.
So what are the x and y?
Which what?
X and y axis, what are those?
So this is the volume prediction, and this axis is the number of colors. So I'm just taking the evaluation I got. I know all the Jones polynomials analytically in figure 8. I know them analytically for K0, I'm just evaluating. Okay, so let me finish. So we've calculated a large, but incomplete data set of adjoint Jones polynomials. It's consistent with the naive expectation of the volume conjecture. And we didn't know this convergence is getting better at small color, so this is interesting. Increasing the crossing number improves the prediction, and we have conjectured a color-dependent phase. We like to check these predictions. We like to see whether there's a way of addressing the volume conjecture using these predictions. And then we can also think about coming up with a better organizing principle for understanding these knots. For example, instead of organizing things by crossing number, perhaps we can organize things with minimal number of ideal tetrahedra to create the volume. That hasn't really worked out too well. And one thing we also noticed was we take the different volumes of knots at various crossing numbers is also a very linear fit. So maybe there's ways to use these linear fits to also make some approximation to the volume conjecture. Recently, there have been various other efforts to connect different invariants among each other for knots. And this Nature paper by the DeepMind group used these data analysis tools, these saliency analysis tools, in order to connect different topological invariants, and based on these connections, we built a theorem. We've been doing some work on associating different topological invariants to each other. So one of the reasons we're doing this is trying to come up with some argument for the smooth Poincare conjecture in 4 dimensions. To find a counterexample to this, some of these open problems in mathematics that typically went to a field level if you ever make any progress on this. The conjecture is that any Homotopian sphere is diffeomorphic to Sn. That's unknown for n equals 4. And this is the only Poincare conjecture still standing, so it's of importance. The relation to knot theory is that if it's false in certain dimensions, you have exotic smooth structures, and these are interpreted as gravitational instantons in various theories, in string theory. So we don't know the answer if n equals 4 yet. The reason this is connected to knot theory is that the smooth Poincare conjecture is that if you can find certain knots with certain properties, then you can find counterexamples. So these are things that we're looking at trying to use neural network approaches to identify candidate counterexamples. So thank you.
Thank you very much, Vishnu, for that wonderful talk, and also for sticking to time. Questions?
So here Can you explain a bit what happens is like they get the conjecture from
So what they did was they fed in a lot of topological invariants, and they tried to associate these topological invariants to each other.
Right.
And they have this saliency measure.
Right.
The saliency measure basically is you tweak your input by a little bit, which directions the gradient is largest in.
Yeah.
So they use that saliency measure, identify that there are a couple of features that are most important. This is sort of analogous to the relevance, generalized relevance propagation that I use in my particular problem. They use these, they identify these features, and then they conjecture some theorem, which they're then able to prove. So this theorem is, I'm told by knot theory people, this theorem is interesting but not super interesting. So it's of moderate importance. And it's interesting that enough that, machine learning can help formulate the theorem. And machine learning didn't play any role in improving it, or formal techniques that made, lean and so on, didn't play any role in improving this. But it at least let you formulate interesting conjectures. I think, if you think about the utility of computers in mathematics, the classification of finite simple groups, in order to write these character tables down, you need computers. And then Pocket able to prove that the four-number theorem, the four-color theorem, was by exhaustion using computers. And the four-color theorem is an important theorem in graph theory. There has not been a similar result of that comparable importance that machine learning played a role in. So it was just baby steps so far.
It will be difficult that machine learning will play a role in the group itself, right? Because there has to be some control over the errors that you make.
Right. The thing machine learning may be useful for example, for SBC4, is identifying a knot, which is a likely counterexample, and then you
For
have
examples,
yeah.
But proving the theorem would be difficult.
That's right. But you can maybe identify the thing you should prove, the statement you should prove.
You guided by conjectures.
Yeah.
What is this paper doing in nature?
I don't know. It made a huge splash. They also have proof of theorem representation theory that was also machine learning inspired.
So in principle, you can have other polynomials too, right?
Yes.
And so you can do something similar with them also?
Yes, we've used Colorado polynomials and Conflict BT polynomials to study relations between these polynomials and other invariants, in particular the slice genus, the Rasmussen S invariant. These, the slice genus, for example, is more directly involved in smooth quantum conjecture in constructing counterexamples. The Rasmussen S invariant has some gauge theory description that that Bonheimer and Rumka looked at, and these polynomial invariants, Colorado polynomials, and so on. They have interpretations in terms of 4D and 5D Yang-Mills theory and 6D02 theory. So the fact that you're using Jones polynomials as a third Hamilton invariant and relating these to other invariants in different gauge theories in higher dimensions, this suggests that certain sectors of these gauge theories may be related to each other in some nice way. And we haven't really found this yet, but we found support that these theories, or polynomial invariants related to these theories, are connected. And we have to better understand that. We don't have, I don't have anything to report on that, but that's something which we're thinking about.
Sure. I mean, towards the end you mentioned this program of finding out examples to the conjecture. So what exactly do you have in mind that when should it do the
Right. So what I have in mind is if you so there's this property called slice genus. It's a topological invariant of a knot. What the slice genus is it's the minimum genus of a surface whose boundary is the knot. That invariant, if certain knots are slice.
No, sorry. Minimum genus of the surface whose boundary is the knot.
Yes. So you think about S1 embedded in S3.
Yes.
S3 is boundary of some ball. You think about a Riemann surface embedded in this ball whose boundary is the knot in S3.
But that's an open Riemann surface.
Yes.
You want to fill that into the disk and then that's the genus.
The minimum genus, yes, is a knot variant. If the minimum genus is 0,
That's called a Seifert surface or something, right? The
Yeah.
surface that bounds the
that's
knot.
right, yeah.
So minimum genus of the sequence.
Yes. The minimum genus is 0. The knot is called slice. If certain knots are slice, that provides a counterexample to smooth concrete conjecture.
Oh.
If certain other knots are not slice, that also provides a counterexample to smooth concrete conjecture. So we tried to train neural networks to predict the slice genus, and we can get predictions at about 95% accuracy. So we can identify, 95% suspicion from the neural network that some knot, which would be a counterexample, is slice or not slice, as the case may be. Then that's not to study further using analytic methods.
And is it easy to understand why is it that this general compact conjecture had to do with the slice genus?
It's not obvious that there are the relations. Another strategy is the slice-ribbon conjecture. The slice knots have a property called ribbonness. Ribbon knots may or may not be slice. By showing certain knots are ribbon, so that happens. So ribbon knot is always slice. So that means the slice genus is 0. If you show a certain knot is ribbon, then you have genus equals 0. So Gukov, Halverson, Mandelstam, and Gula last year had a paper that used transformers and reinforcement learning in order to perform actual moves that convert a knot to a ribbon form. And they killed a number of potential counterexamples to the compact conjecture by showing these knots were ribbon.
Maybe I can ask
Yeah.
a question. So one naive question, you showed 3 different nonlinear functions.
Yes.
So are your results dependent on those functions, or
So these
yeah.
these nonlinear functions,
Right.
they work pretty much the same. You put
So-
any of these in your neural network as your activation function, you get results that are essentially unchanged.
I see. So there are no biases associated with which one you pick.
Not really, no.
Any questions? Okay, so if not, we thank Vishnu again.